Hi, my name is Smriti Rajan, and I work this summer with my mentor, Miss Laree Boumer of Simone Fraser University. Today, I'm going to be talking about how the accuracy of the CRISPR-Cas9 gene editing technology I'm sure you've all heard about can be improved. So we'll start by looking into the current CRISPR model and why it needs fixing, then introduce a new model that is the basis of my research project. What makes this new model special is the use of PPGs, which we'll then talk about, and finally, everything that I did and found. So here is the current CRISPR model. After identifying a mutated gene that needs correcting, scientists design a complementary guide RNA and introduce it into the body alongside a Cas9 nuclease taken from bacterial genome systems. The nuclease, which is just a fancy way of referring to an enzyme that cuts DNA, then follows the gRNA to the target gene, and you can kind of see in this first picture how that works. So in this model, a scientist's job is done after introducing the CRISPR components into the organism, after which the Cas9 enzyme will cut the DNA, and then either the organism's natural repair mechanisms will seal the DNA back together without the mutated gene, or a healthy copy of the gene can be introduced to take its place. And because scientists have no way of intervening afterwards, the current CRISPR model cannot prevent the off-target effect. Obviously, there are only 4 bases, A, T, G, C, and these form 3 billion base pairs in the human genome. So it is inevitable that certain regions of our DNA are similar or the same in sequence. So what oftentimes happens is the gRNA guides the Cas9 enzyme to the wrong area, and fatal cuts can be made to the DNA. This limits the use of CRISPR in clinical settings, so the need for increased spatiotemporal control is critical. Let's take a look at some of the current attempts at achieving that. Models which give scientists external control over the CRISPR system have been developed using nanoparticles, magnetic fields, and light as stimuli. I won't get into the details, but light has been proven to be the best stimulus overall, as it is non-invasive and more effective, among other things. And the way that light has been used most recently is to remove some sort of molecule from gRNA, which will act as a temporary inhibitor until then. These molecules can be biological molecules like oligonucleotides. However, oligonucleotides require quite high doses of UV light to undergo photolysis, making them incredibly ineffective. Also, leakage of the activity was observed in the dark when experiments were conducted, which brings me to PPGs, and those are the molecules that are used in the new CRISPR model, which this study was built upon. The use of PPGs in designing an inducible CRISPR model was originally proposed by Moreau Zamori and their colleagues. This image I made details how it works. Essentially, the extra step of removing the PPGs via light is added. Until then, scientists can confirm that the nuclease is in the correct position and act accordingly. The nuclease is activated by light, so until receiving that stimuli, we can prevent the off-target effect altogether. So what are PPGs and why are they so special? PPG stands for photoremovable, photocleavable, or photoactivatable protecting groups. Those are just some of the names you might encounter for these molecules, but regardless of the name, they can cage or protect another molecule until they are photoremoved. They have been used before to aid a number of reactions from drug delivery to transcriptional and translational control, but their general use is the temporary inactivation of substrates. These substrates can be anything, but this model is going to focus on their ability to inactivate RNA, or more specifically, CRISPR's gRNA. Now that all of that background information has been established, we can talk about what my study actually was, which was identifying and evaluating PPGs. The first step for this was finding PPGs that had been previously shown to have a strong affinity for DNA or RNA, and understand what exactly makes a PPG effective. And so from all that preliminary research, I was able to outline these 4 criterion. Obviously, not every criteria will be met by every PPG, but the idea is the more of these that a PPG meets, the better it will be. And since the first criteria had been proven for these molecules previously, my main goal was identifying absorption at various wavelengths. The above 400 nanometer constraint, which you see, is consistent with what wavelengths of light are safe for humans. Anything below 300 nanometers has been shown to be absorbed by any organism and cause harm to its membranes and DNA. And then UV light, which ranges from 100 to 400 nanometers, is also obviously harmful to humans as a known carcinogen. So I recommend molecules with strong absorption at wavelengths above 400 nanometers. And then the other criteria listed here are also very important and avenues for future research. However, we're going to skip over them for now as they are beyond the capabilities of quantum chemistry softwares, and so were not calculated in this study. The quantum chemistry software ORCA is what I used in the study, and I ran a time-dependent density functional theory calculation on each of the molecules selected for this study, which are pictured here. And so TD-DFT calculations can reveal the absorption spectrum of molecules. That phrase ab initio just means that it relies on basic and established laws of nature without additional assumptions or special models. Also worth noting is that the molecules used in the study are not so large that the outputs will be significantly inaccurate, and all of these factors can just go to show that this is a viable method of evaluating PPGs. And then the black image here is the input file, which I used for all the molecules, with the only difference being the Cartesian coordinates of each molecule, which were extracted using the ChemDraw software. If you are interested, I can break down each line of the input file, but we're going to move on to my results for the sake of time. The first molecule, which I ran, was 3-nitrobenzaldehyde, and the image to the left is what ORCA generated for me. The one to the right is the spectrum constructed from this data using the software multi-WFN. You can see that absorption peaks at wavelengths 170.6 nanometers and 218.1 nanometers, which are obviously not nearly high enough. And at the wavelengths which we wanted to see high absorption, oscillation strength and the molar absorption coefficient, which by the way correspond directly to the relative absorption, are close to zero. Right away, we can see that this molecule is not suitable. For those of you interested in how accurate this generated spectrum is, the spectrum for this molecule has been previously calculated using physical means rather than software and is online. You can find it with a quick Google search. And the wavelength at which absorption peaks in both my graph and the existing graph is off by only 6.2%. And since we don't really care about the exact number, but rather the range of wavelengths at which the PPG will function well, that percent error is really good and further proves that this is an effective way of evaluating PPGs. Moving on, here are the results for 4-methoxy-7-nitroindolene. They were also disappointing with the max absorption occurring at 185 and 284.8 nanometers. So this isn't really the best PPG either. Finally, 1-acetyl-5-bromo-7-nitroindolene was evaluated, and you'll notice that the picture looks a little different. This is a spectrum that was previously reported by Morris and Jay and their colleagues. Unfortunately, the calculations were too expensive for my computer, as in they consumed too much CPU power to complete the self-consistent field or SCF convergence, which must occur before absorption spectrum generation. I suspect that it was due to the peak performance occurring at higher wavelengths than the other molecules. Regardless, the results shown here prove that this molecule is actually very effective and can be used with the revised CRISPR model. Obviously, other properties as listed in the criteria I created need to be evaluated still. However, this is a good starting point for future research. And maybe eventually we can fully flesh out this revised model and increase the presence of gene editing therapies for combating fatal genetic disorders. As a result of that increased demand, manufacturing can occur on a larger scale, resulting in lessened costs for patients and suppliers of gene therapies. The future is bright for CRISPR, and the first step to that future is making it safer. Before I open up for questions, I just want to thank the Talaria program directors and my mentor once again. This has been a really rewarding experience for me and an opportunity to pursue formal research despite my age and gender. So I'm really grateful to have had the opportunity to learn all that I did.